So we've learned about complex numbers. We used our knowledge of complex numbers to define and learn about complex vectors. Then we used our knowledge of complex numbers to learn about complex matrices. Now we can complete our studies by thinking about complex vector spaces. If we have a complex matrix that's m by n, we can view that matrix as a machine that goes from Cn to Cm. And we previously studied the 4 fundamental subspaces of our matrix when everything was a real number. And now we can do the same exact studies, except the one change we need to make is instead of in the 4 fundamental subspaces, pairing the null space with its orthogonal complement given by the column space of the transpose, we replace the transpose operator with the orthogonal, or with the conjugate transpose operator. So the orthogonal complement of the null space of a complex matrix is the column space of the conjugate transpose. On the other side, if we're studying the column space, its orthogonal complement is no longer the null space of the transpose, it's the null space of the conjugate transpose. So all we have to do to continue our studies here is replace all of those transposes with the star operator, and we have the exact same theory on our hands. The dimensions are still given for the column space and the column space of the conjugate transpose. Those are still the rank of the matrix. The dimension of the null space is still the nullity, and the dimension of the null space of the conjugate transpose is the nullity of the conjugate transpose. And we still have the rank nullity theorem, which tells us that the rank plus the nullity equals the number of columns, and also that the rank plus the nullity of the conjugate transpose equals the number of rows. So everything we've said before about the fundamental subspaces applies for complex matrices as long as we replace our transposes with the star operator. So again, this is the same as before with A transpose replaced by A star. Now, why are we bothering with any of this? Well, the reason is that it turns out that if we care about eigenvalues, which we're going to start to do more and more, we cannot ignore complex numbers. Here's an example of a perfectly good 2 by 2 matrix. In fact, this matrix isn't even that bad. The columns are 0, 1 and -1, 0. It turns out that the eigenvalues of this matrix are complex numbers that aren't real, -I and I. Well, we should not be intimidated because we can just do everything we've been doing except make the appropriate replacements where we need to. So what are the eigenspaces? Well, the first eigenspace, E sub A of -I, is the null space of the appropriate characteristic matrix, -I times the 2 by 2 identity minus A. And in this case, we can find a basis for that space, and that basis is given by the complex vector -I, 1. What about the other eigenspace? The other eigenspace, E sub A of I here being the second eigenvalue, this is the null space of the other characteristic matrix, the imaginary number I multiplied by the 2 by 2 identity minus A. And when we find a basis for the null space here, we get the span of I, 1. So a complex vector as a basis for this complex eigenspace. So since we care about eigenvalues, we can't ignore the theory of complex numbers because a perfectly good real matrix might have complex eigenvalues that aren't real numbers. So we have to incorporate this into our theory in order to complete our theory.